Doing pretty well. How about yourself?
Oh, not too bad. So far, so good. All right, I'm
That's
getting your
awesome.
video ready. So by all means, say hi and introduce yourself.
Totally. So, hi everybody. My name is Igor. I work at Cash App. I'm an Android engineer. I'm very excited to be here. Albeit I'm at home. I'm not in Chicago, but yeah, it's awesome so far, and I hope you're enjoying it. So my talk is recorded. Check it out. If you have any questions, I'll be here after the talk to answer them. And of course, hit me up on Slack. And yeah, well, enjoy.
Awesome. Yeah, remember, this is the Slack channel for questions. So you can ask those during the video, and Igor will be around to answer them. And then if there's any left after the video plays, we will tackle those live. And with that, I will start the video.
Hey everyone, my name is Igor and I work at Cash App. I'm an Android engineer, and today I'm going to be talking to you about protocol buffers, Kotlin Multiplatform, Wire, and a few other magical tools that I hope can help you step up your wizardry game. So let's get to it. First of all, what exactly are protocol buffers? So imagine we're writing an application about dinosaurs. We have our server pod that's written in Kotlin that lives in the cloud, and we want to send data from that server to our iOS app, which is naturally running Swift or Objective-C, whatever. So how exactly are we going to pass an object from our Kotlin server to our iOS app? And the answer is that the process of converting something that is platform specific to like a platform agnostic format is called serialization. And format that we're looking for, therefore, will be called the serialization format. One of the most widely known and used serialization formats nowadays is called JSON. So let's see how our dinosaur object will look like if represented in JSON. So you can see that it's pretty easy to understand what's going on here. And JSON actually is pretty great. First of all, JSON supports a large range of different data types that different programming languages use, such as numbers, strings, arrays, and complex objects. Second, JSON internalizes its schema. So you can see that the keys or like the field names, they're added to the message itself. So it makes it pretty easy to map the data in the JSON to be like a class or struct to populate the data. So this is pretty cool, right? And in general, JSON is designed to be human readable. It's text-based, the schema is included. So generally, if you're transferring JSON over the network and there's like no encryption for some reason, then you could just read those messages. So they're like easy to debug and so on. But JSON comes with a few downsides as well. So first of all, to map a JSON message to a platform-specific representation, you have to write code, you have to write classes by hand, and you have to do it on all platforms. And this can be tedious and error-prone. Second, that the schema, or basically the keys of the message, are very loosely defined. So you could just extract them from looking at the message. But because certain fields can be omitted, if there is no data for that field, you can't really reason about like the complete schema of the JSON message. And lastly, because JSON is text-based and because the schema is included in the message itself, JSON messages tend to be relatively large. So an alternative serialization format proposed by Google is called the protocol buffers. And the short for protocol buffers is actually Protobuf. We'll be using those interchangeably. So let's see how we can represent our dinosaur object in the Protobuf representation. So you can see how it looks here. And actually, the thing that you see here is just the schema for that message. So the schema in Protobuf messages is explicit. So you have to declare what the fields are, and you also use something called tags, which are numeric values attached to every field. So in order to turn a Protobuf message to its platform-specific representation, you usually rely on code generation. And there are code generators available for a lot of different programming languages, where you could just take a message in the Protobuf format and generate like a class or a struct to represent that message on a specific platform. And lastly, because we're not including the schema in every message, so the only thing we include is the actual data and the tags for the fields, the messages tend to be much smaller. So let's see how we can represent our dinosaur object in the protocol buffers format. Well, this looks like a bunch of gibberish, right? Well, the thing is that protobuf messages are binary, so those are just a byte string represented in the hex format. But even though it's just row bytes, it's actually quite trivial to read this string and understand how the data is represented in it. So let's just quickly go over the fields. So you can see that we use the first 2 bytes to represent the first field called name. So the first byte contains the tag for that field, number 1, and it also encodes the data type of that field. So here specifically it's a string. So that means that the second byte has to encode the length of that string. And naturally, the next sequence of bytes are just the individual characters of that string. So protocol buffers uses UTF-8 to represent strings, and because for this specific string every character is present in the ASCII table, we actually need just 1 byte to represent each character. Next up is the length meters field. You can see that first byte is used to encode its tag and also the data type, and the next 8 bytes or 64 bits have a 64-bit number, so we use it as a double. Here it's just a 64-bit number, which is basically like a platform-agnostic term. Next is the mass kilograms field, which is also a 64-bit number. So you can see that 1 byte we use for the tag and next 8 bytes for the value. And lastly, an enum field, period. So we use 1 byte to encode its tag and another 1 byte to encode its value. So the thing is that in Protobuf, every enum value has its own tag, which makes it really easy to represent it in a protocol buffers format in a very efficient manner. So as I mentioned, Protobuf was first proposed by Google, and Google ships a large suite of tools to accompany protocol buffers like code generators and so on. And Wire is a suite of tools for working with Protobuf built at Square. So why exactly did we need to build our own set of libraries to work with protocol buffers? So Wire was first designed to produce Java code optimized for Android. So if you remember back in the day, there were more strict limitations for how many methods an Android application could have and how many fields. So every method counted. And it turned out that Google Code Generation produced very large Java files. So it was quite prohibitive to use protocol buffers on Android. And Wire tried to address that problem, generating much smaller Java files. But later on, we added Kotlin into the mix, and Wire started producing Kotlin files from Protobuf messages. And just very recently, we added Swift support, which is another exciting addition to the mix. But the most important part for this session is that Wire plays really well with Kotlin Multiplatform. And for the rest of this session, I'm going to guide you through a demo that I prepared in order to show you how we can build a server-client applications that use Kotlin Multiplatform with Wire to communicate through protocol buffers. So let's start. First of all, let us just sketch the modules of our application. First, we'll use a Protos module. So that module is going to be shared between all of the parties in our multi-module application. Protos module will include our Protobuf definitions, so the actual proto messages, and it will use a Wire's Gradle plugin to run code generation and produce artifacts that can be used by different applications. Then we'll add a server app that will rely and basically depend on the Protos module. We'll add an Android and iOS apps, and also add a command line application, just for doing some experiments with our Protos. Let's start with configuring the Protos module. We'll start with the build Gradle file. You can see that we're using the Kotlin Multiplatform Gradle plugin because Protos is going to be a multi-platform project consumed by different parties in our system. We'll use a CocoaPods plugin for Gradle. So CocoaPods is a dependency management framework for iOS. You can think about it as like a rough alternative to Gradle, but just like the dependency management part of Gradle. So this is what CocoaPods achieves for iOS apps. And lastly, as I mentioned, we'll be using the Wire Gradle plugin to do some code generation for us. So we'll declare two targets in this module, the JVM target and the iOS target. iOS will basically be used by our iOS app, but the JVM target is going to be shared between our server and the Android apps. So I have to mention that it used to be not really straightforward to configure iOS targets in Kotlin Multiplatform before Kotlin 1.4. Well, Kotlin 1.4 introduced a couple new Gradle properties that make it much easier to declare targets. So Kotlin does a lot of basically figuring out the architectures and the individual targets under the hood. So the DSL is much simpler. You can just use iOS as the target, and Kotlin will pick the right sub-targets for you. So you can use those Gradle properties. They're experimental for now, but at some point they'll become stable. Next thing we have to do is to add the generated sources folder that Wire uses to put the generated code into to our sources of our module. We need to do that so when the compilation happens, it will pick up the generated code and compile it as well as the sources in our module. And we also add a dependency to a Wire runtime module. So this is a very small multi-platform library that contains code that the generated code depends on. We'll add some basic CocoaPods configuration to the mix. And lastly, we'll configure the Wire Gradle plugin. As I mentioned, Wire supports multiple languages as output, so we have to tell Wire that we actually want Kotlin for this project. So we configured Gradle in this plugin, and the next step is to put our proto message definitions into source main proto directory. So this is the period enum here, and this is the actual dinosaur message that we'll be using to generate code. So because Wire Gradle plugin hooks into the build pipeline, whenever you build the module, the Wire Gradle plugin will actually pick up the Protobuf messages and generate code. And because that code ends up in the sources, the compiler will then compile that code, producing the final artifacts that can be used by other modules. And this is like an example of the code that Wire generates. You can see that it's a simple Kotlin class with public vals that we can use in our code. One more thing we have to do is call the podspec Gradle task. And this one generates something called a podspec file that CocoaPods use to root the dependency management. And the important thing here to note is that CocoaPods will add like a script phase to the Xcode build system. And this will allow the Xcode build to link into Gradle, which sounds pretty cool, right? So whenever you build your iOS application with Xcode, under the hood, it will actually call Gradle to call this sync framework task, which ensures that there's like a library for Protos module that the iOS app can rely on. So we're done with the Protos module. Let's jump to the server. We'll use Cater-Natty for this example. So we'll be using just the Kotlin JVM Gradle plugin and the application plugin. And we'll also use the Shadow Jar plugin because at the end we want to package our server as like a fat jar, basically the code for the server and all of its dependencies, so it's deployable to something like a cloud. And we'll add the dependency to our Protos module so we can reference that code in our server app. And you can see that the server app is actually pretty simple. It just creates a dinosaur object in memory and returns it as bytes in the response for the dinosaur endpoint. You can see that we use the dinosaur adapter class that allows us to take an object and encode it in bytes according to the Protobuf format. Next is the Android app. We're using some standard plugins here, and we also add the dependency on our Protos module. We'll be using Retrofit for basically for networking because it's easy to set up Retrofit to understand Protobuf and wire messages. And in the spirit of a well-known anti-pattern of having everything in our main activity, we'll be setting everything up in our main activity. So you can see that we're setting up our retrofit client. We use the wire converter factory that allows us to basically tell retrofit that it'll be getting some protobuf messages and parse them correctly. After that, we create a coroutine to call our server on the background thread, obtain the dinosaur object, and pass it into the dinosaur view, I'm sorry. And dinosaur view is just a very simple composable function with just like a vertical stack of text views. I definitely need to find a designer for this project because right now it doesn't look good, but it works well. So yeah, it just does the job, and it's awesome. And the last part, arguably the most interesting, is the iOS app. So how exactly are we gonna use our Protos module, which was written in multi-platform Kotlin, in the iOS app? So let's start by configuring the Cocoa pods. So we create a pod file, which just declares dependencies for Cocoa pods. And you can see that we're adding a dependency to the Protos module. And we do it by just referencing the location on the local file system to the Protos module. Then we run the pod install task, and pod install would generate all of the files that we can start using in Xcode to build our iOS application. So let's get to it. Let's write some Swift code. So a huge disclaimer, I'm not an iOS engineer. I don't know what I'm doing. I have no idea. So if any of that Swift makes you cringe, I sincerely apologize for that. So I'll be using something called dinosaur resource, which is an observable object. And dinosaur, basically an observable object, has like a property that like the view layer can observe and redraw when it changes. And we use this property here in order to do some networking, by the end of which we obtain the bytes containing our dinosaur object. And then we'll try to convert those bytes, which is data. So we'll try to convert that data into the dinosaur object. And again, we'll be using the dinosaur adapter class that Wire generated for us. And it has an ability to actually work with the data type in Swift and convert it to an object by parsing those bytes. Then we have a content view, which will be observing the dinosaur resource. And whenever the dinosaur object is available, it will just pass it to the dinosaur view. And dinosaur view looks very similar to its Android counterpart. So this is just a Swift UI view, which again is just a vertical stack of text fields, which print out the fields of the dinosaur message. And there we have it. So those are both our apps that we wrote in Swift and Android. They use a shared data layer written in Kotlin Multiplatform. They talk to the server that uses the same data layer. So this really feels like magic to me. We basically achieved zero domain layer duplication, and we just focused on our business logic on two platforms on the UI layer, and we just left everything else to protocol buffers. That's pretty cool, right? And to talk a little bit about Wire, it's pretty awesome as you can see. It can do a lot, but we're continuing to make it more awesome. So as I mentioned, the latest release actually shipped with Proto 3 support. So we didn't talk about it during this session, but there are two kind of different formats, different versions of protocol buffers, Proto 2 and Proto 3. For a long time, Wire only supported Proto 2, but Proto 3 is something that's already available and can be used with the latest version of the library. Then I already brought up the Swift support. JetBrains are working really hard to improve the ergonomics of using Kotlin code in Swift. So if for some reason you find that it's hard to use Kotlin code in your Swift apps, then you could just use the generator and and basically rely on the Swift generated code. And lastly, gRPC is a networking format based on HTTP2 And it basically benefits from protocol buffers code generation to establish networking code. And gRPC is something that Wire supports for JVM platforms, but we really want to get to a point when we have support for iOS as well. And we can use gRPC between different platforms. So yeah, that's pretty much it from my end. I hope you enjoyed it, and thank you for your time. Bye now.
Awesome. That was great. Thank you very much, Egor.
Thanks a lot.
Let's see. It does not look like you had any questions. Come on, folks. Don't be shy. As anyone thinks about questions, or if you come up with any questions throughout, remember that the Slack channel is below. Egor will be around for the conference to answer any of your questions. So if you can't think of anything on the spot right now, feel free to type them in later. Egor, thank you very much for being a part of this. Very much appreciate your time and energy.
Thank you so much, John. Yeah, love to be a part of it. It's been awesome. And yeah, folks, if you have any questions, I'll be on Slack to answer them. Please feel free to talk to me about Wire, Square Open Source, or Cash App. I'm happy to answer any questions you might have.
Sweet. All right. Well, thank you, everyone. We will be back in 9 minutes. Remember to stop by the expo, say hi to all of our sponsors. And hey, Ryan.
Oh, whoops. Hey, everyone. Excited to see you at the next talk.
Yeah, so we will be back in 8 minutes. So ask your questions in Slack. Egor will tackle those and visit the expo, say hi and thank you. And we will see you in a few minutes.